Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Waisakir bin Azari and my metric number is 202459. And my title of the report is Insulation Rod with one closed end. And the equation used is Laplace equation. So, we will get to the engineering problem, which is a very long cylindrical rod with one end at s equal to 0 is positioned along the positive x-axis. The rod is so long that it will ignore any consequences owing to its right end. The sides are completely sealed so that no heat will enter or escape through. At time t equal to 0, because the rod temperature is 0 Celsius, it immediately the rod left and has increased its temperature to U, which is some value, and subsequently had at this temperature. The initial boundary value problem describing temperature of the function U in the bracket xt at point in the rod is this differential, which is differential of U respect to T, and K, which is the thermal diffusivity K, and the double differential of the U respect to S, which is S more than 0 and T more than 0. And the second equation is when the x equal to 0, the equation will be equal to U naught. And the third equation is when the T equal to 0 and the equation will be 0. So we get to the method. When we apply the Laplace transform to the partial differential equation, and we will use this property, which is this property. L is the sign of the Laplace transform with the differentiate of f respect to t, and the s capital F and minus 2f 0, which is 0 is time. Thus we obtain the equation s prime. This equation is obtained by using all of this equation, which is this equation of t equal to 0 we obtain by the third equation, and this one we obtain by the first equation. So since the Laplace integration and differentiation from x are independent with respect to t, we are exchanging the right order of operation, and it will become like this. So where the initial condition 3 will also use, which is this, and since derivatives only are available as for remaining x, we replace the partial derivative with ordinary derivative, which is it will be something like this, and the condition is s more than 0, and we will state this equation as the equation number 4. When we take Laplace transform of the boundary condition 2, we obtain this equation by, which is a condition of equation 2, this one, which is we change the t to s and we divide the u naught by s, and we will obtain this equation. And a boundary condition to accompany differential equation 4, which is this. A generalization of the equation 4 will be something like this. And because the function of u must remain bounded as x become infinite, so also must x prime in the bracket x comma s, we must therefore set a equal to 0, which is this function will be gone, in which case 5 requires b equal to u naught over s, which is the function 5 we will change it to b. Thus we will just substitute it and it will become like this. the inverse transform of the function can be found in the table. So we inverse this equation, and this is the function of the inverse Laplace transform, and we obtain the u naught ERFC in the bracket x over 2 square root kt, and we know that the ERFC in term of x is equal to 1 minus ERF x, which is the value of this is the value of ERF x 1 minus 2 over square root pi, and they integrate with x to 0 and exponential to the power of negative to the power of 2 du. And when the 1 minus of this function, we will obtain infinite, the function between the infinite to the x. When we make a graph, so we choose the different time, which is time 1, time 2 and time 3. We will see that when the x is 0 and t is 0, the temperature will be positive, and this one indicate the absolute change in temperature at the end of x equal to 0 from 0 Celsius to u, and u is instantly flat at every point. The point on the road have shown a plot of u, the function of u as t for the different fixed value. That's it. Thank you.